Hi, everybody. Welcome to Introduction to Hypothesis Testing. This is going to be the final topic in this course. We're going to have 4 lectures on it. This is the first one where we're going to lay the foundation, and we'll begin doing actual problems in the next lecture. So let's look at these 4 normal distributions with shaded areas. And my question is, which of the following curves, bell curves, shades an event that is the rarest? Which one is the rarest event? And you should look at the shaded areas and recognize that the rarest event, and it doesn't matter if it's on the right side of the curve or the left side of the curve, but a rare event is one in which the probability is smallest, and that occurs when the area that's shaded in is smallest. So this is the one with the rarest event because this piece of area here is smaller than all the other shaded pieces of area. That's something that we're going to be using in this topic of hypothesis testing. So I want to do a little bit of review on probability because it's very much a big portion of how to solve a hypothesis test problem. So let's look at a question that we've already seen before. Pregnancy lengths are normally distributed. The mean is 266 days. The standard deviation is 16 days. So we draw our normal distribution and we label the center with 266. So pregnancy lengths that are long are on the far right, and pregnancy lengths that are short are on the far left. And so we have the bulk of the pregnancy lengths somewhere in the center near 266. Let's suppose that a woman gives birth 308 days after conception, which would make her pregnancy length 308 days. That's going to put it way over here on the long side. What's the probability of a pregnancy lasting 308 days or more? So here's where 308 is. 308 or more represents the area to the right of 308, so we will shade that piece in. And we'll go to our calculator, normal CDF, and for a lower, we would put 308, upper E99 for positive infinity, mean 266, standard deviation 16. And if you need a refresher on how to do that, I'm going to go to the calculator now. So second distribution, normal CDF. We're going to put in 308 here, E99 for the positive infinity, 266 here, and 16 for the standard deviation. And the probability comes out as 0.0043. Okay, 0.0043, which is a small probability. Let's take a look at another question involving probability. Recovery times for a common surgery are normally distributed with a mean of 30 days and a standard deviation of 5 days. So here's our normal distribution with the center at mu equal 30. A hospital claims a new post-operative protocol reduces recovery times. A sample of 100 patients has a mean recovery time of 28 days. So this mean represents the mean of the sample. So this 28 is the value for X bar. What's the probability of a mean recovery time of 28 days or less? So now we recognize that this problem is providing us with a sample, and the question is asking us about the mean of that sample, the probability of the mean of that sample. And so we need to take that additional step that we saw in the previous few lectures ago, where we had to calculate the standard error. This problem asks us to calculate the probability for a sample mean, so we need to find the standard error first. Because we're going to be using the sampling distribution, not the population that we have here. We're going to be using the sampling distribution to calculate our probability. So let's build our sampling distribution by calculating the standard error. We're going to take the sigma, which is provided to us as 5, and divide by the square root of n. 5 divided by the square root of 100, and this will give us our standard error of 0.5. So now we can go to our picture for our sampling distribution. This is not the population now, this is the sampling distribution. And we label the center with the same mean. Remember, the value for the mean, the mean of the population is the same as the mean of the sampling distribution. We label that in the center, but the standard error now is the measure of the spread of the sampling distribution and not the standard deviation. Okay, the x bar of 28 is what the problem provided us, and we were to find the probability that the x bar of 28, I think it was phrased, what's the probability of a sample mean being 28 days or less? So we were kind of calculate the area to the left of 28. That's a really small piece of area. So we're going to go to the calculator again. Low is negative infinity this time because we're working on the left side of the curve. Upper is 28, mean 30, and the calculator says sigma, but we know that we have to put the standard error in there. So we're going to be putting in 0.5. We know we're putting in the standard error because we're working with a sampling distribution. So you go to normal CDF and you put those numbers in and you get a probability that is in scientific notation. So let me show you what that looks like. So let's put those numbers into normal CDF. Negative E 99 to an upper of 28 and a mean of 30 and a standard error of 0.5. We paste it. And this is in scientific notation. You notice the E negative 5, E minus 5 on the far right. That means we're going to take this decimal point and move it 5 places to the left and fill in those remaining spaces with zeros. So I'm going back to the slideshow now. So in scientific notation, we take the decimal point right here, move it 5 places to the left, and fill in those spots with zeros. And when we round this to 4 decimal places, if we were given this problem on an assessment, like a MyOpen Math assignment, we would round this to 0 because this 3 here tells us to keep the 0 in the 4th place as it is. So the answer to this question would be 0. Look, if we were to need to round it. Looking at the actual number, though, we see that it's not actually 0. It's just a very, very small probability. But it also, like the previous example with the pregnancy lengths, it's considered to be a really rare event. So rare events are important. Sometimes they happen by chance, but there's oftentimes cases where rare events are not actually happening by chance. Small probabilities suggest results are unlikely due to chance. These results prompt further investigation or changes in practice. So an example, we were looking at recovery times for patients getting a common surgery, but they were getting a new postoperative procedure. If the recovery time with this new post-operative procedure consistently leads to recovery times much shorter than the average population mean 30, it may signal its effectiveness. So we got a sample mean of 28 in that previous example, which was less than 30. And if that seemed to happen over and over again, it may indicate that the postoperative procedure truly is working and it effectively reduces the recovery time for these patients. So in the center, we have the established understanding of what the recovery time is, the population mean recovery time. This is a sampling distribution. And generally in the middle, we have our common outcomes, but far on the far left or on the far right, we have our rare outcomes. When those rare outcomes happen, it gives us reason to consider that what we're testing, in which case, in this case, it's a post-operative procedure, could truly be an effective an effective intervention. So it's so much different than 30. It came out to be such a rare occurrence that it may indicate that it truly is effective. Okay, so an X bar on the far left, if this is rare, it might indicate the intervention is successful. So in hypothesis testing, we have a process that formalizes the decision-making process. The problem starts with writing two hypotheses. And I'm going to generalize these two hypotheses here. And in future problems, we will use more specific wording for the hypotheses. But the two hypotheses are the null hypothesis, which we symbolize with the letters HO, and it indicates that the treatment has no effect. So in the previous example, where we were testing post-operative recovery or recovery after a post-operative intervention, the treatment has no effect would indicate that the post-operative intervention doesn't do anything. Then we have the other hypothesis. It's the opposite, the alternative hypothesis, and that is symbolized by HA. And in that case, the treatment is effective. So we have these two sides of the coin, two beliefs. One, the null hypothesis, the treatment has no effect. And two, the alternative hypothesis, the treatment does have an effect. It is effective. That's where the problem starts, or that's where the hypothesis test process starts. Then we go through a statistical analysis. At the end of that statistical analysis, we decide which of these two hypotheses is correct. So at the start of a problem, you don't know if it's going to be the null hypothesis or the alternative hypothesis that wins in the end. But by the end of the problem, you have got your statistical analysis conducted and you could make a decision as to which one is correct. So we are going to use healthcare examples to explore this framework. First, we are going to compare the hypothesis testing procedure to the judicial system. In the judicial system, when an individual is accused of committing a crime, a trial is conducted to determine if there is evidence to convict the individual. In the beginning, the defendant makes a claim of their innocence. In a hypothesis test, we say that the treatment has no effect. So somebody's innocence is the same as saying the treatment has no effect. This is before any analysis is conducted. We make the assumption that what we're testing, the treatment, doesn't do anything. And similarly, in a judicial system, we make the assumption that the person is innocent until we get to see some evidence. Throughout the trial, we assume the defendant is innocent. They are presumed innocent. And through a hypothesis test, we also assume that the treatment has no effect. And we could be talking about a treatment, or we could be talking about a vaccine, or we could be talking about a new drug. We're just assuming it has no change on, on the sample. The prosecutor's task is to present evidence to cause the rejection of the assumption of innocence, a rejection of the claim made by the defendant. The defendant claims their innocence. The prosecutor attempts to disprove that innocence, reject the assumption of innocence by providing evidence. We do something similar in hypothesis testing. People conducting medical research or people conducting any hypothesis test, they have the job of using sample data similar to the evidence in a trial, sample data to show that whatever is being tested, treatment, drug, vaccine, a product's effectiveness, is truly effective. This is the rejection of the initial assumption. So remember, the initial assumption was that the product, treatment, vaccine, drug is not effective. Well, if our sample data can show otherwise, we can reject that initial assumption, and we could say that the initial assumption was wrong. The two hypotheses, HO and HA. In a hypothesis test, the null hypothesis is a claim about the population, like the defendant in a trial. So the null hypothesis is a claim about the population. It's saying that the current population parameter is true. The alternative hypothesis is the counterclaim about the population, like the prosecutor in a trial. The prosecutor tries to show the defendant is guilty. The alternative hypothesis looks like this. The population parameter is not true. And we do this by looking at the sample evidence. An example of sample evidence, and the example that we are going to be using in this course, is X bar. Sample data is used to attempt to disprove the claim in the null hypothesis and prove the alternative hypothesis is true. In this course, the current population parameter that we are going to be using will be mu, and the sample evidence will be presented as X bar. There are other types of hypothesis tests that can be conducted. We're not going to be able to get to all of them this semester, but they involve other types of population parameters and other types of sample data. We will get to one at the end of the set of lectures. This will be our final lecture. We are going to be doing one more hypothesis test that's not based on mu and uses a different sample data, but you'll see it when we get there. Okay, the two hypotheses, HO and HA, let's look at example 1. The null hypothesis, HO. We're going to make a claim about the population parameter. The population mean systolic blood pressure of patients taking a new medication is the same as the population mean for patients not taking the medication. In other words, the medication has no effect on systolic blood pressure. Okay, this piece right here, this explanation, is not officially part of the null hypothesis. I'm adding it here for explanation. So if the null hypothesis says that there is no effect the treatment has no effect, the vaccine does not work, the drug doesn't do anything, the new product isn't any better than the old product. The null hypothesis states that, but the alternative hypothesis does the opposite. The alternative hypothesis, the population mean systolic blood pressure of patients taking a new medication is less than the population mean for patients not taking the medication. So here we're saying that there is an effect. The drug vaccine process, treatment, product is better than the current population parameter. There is an effect. So, in other words, the medication has an effect on blood pressure. Also, this piece, not officially part of the way we word an alternative hypothesis, but I'm putting it here for explanation. Example 2, let's do something similar with healing time. The null hypothesis, the population mean. Okay, we're making a statement about the population parameter here. The population mean healing time for patients using a new wound dressing is the same as the population mean healing time for patients using the standard dressing. The new wound dressing does not reduce healing time. Okay. HA, the population mean healing time for patients using a new wound dressing. This time, we're using the term less than the population mean healing time for patients using the standard dressing. In other words, the new wound dressing reduces healing time. So some explanation, this and this, not officially part of the way we state alternative and null hypotheses, but it offers an explanation here. So see the similarity between the previous example and this example. The null hypothesis always says that it doesn't matter what the variable is. The healing time in this case is the same. And the alternative hypothesis says it does matter. The healing time is less than. So the variable changes from problem to problem. Here we're looking at healing time for a new wound dressing versus healing time for a standard dressing. In the previous example, we looked at new medication. So we looked at a new medication versus not taking the medication at all. So it changes from problem to problem, but what stays the same is the null hypothesis claiming that there is no effect, and the alternative hypothesis claiming that there is some kind of effect, either less than or perhaps greater than. Let's do a third example. This time we're doing a greater than example. The null hypothesis states again that the population mean, whatever we're referring to, is the same. The population mean increase in cardiovascular endurance for patients undergoing a new exercise intervention is the same as the population mean increase for patients following the standard exercise protocol. In other words, the new intervention doesn't increase cardio endurance. The alternative, we state that there is a difference. The population mean increase in cardiovascular endurance for patients undergoing a new exercise is greater than the population mean increase for patients following the standard exercise protocol. The new intervention increases cardio endurance. So we see this similarity across all these problems, and that's going to hold true for all the null and alternative hypotheses that we see moving forward. They are claims about population parameters, and the null claims no change, while the alternative claims that there is some kind of change. Now, if you notice, all of these are claims about the population, but what we're going to be using in our statistical analyses is sample data, which makes this hypothesis test topic a form of inferential statistics. We're using sample data to either come to a conclusion for HO or come to a conclusion with HA, but sample data is what's going to drive our decision making. So let's look at the decision. Let's imagine a jury making decisions in a trial. And here we have one side of the coin, sample data being provided is weak sample data. HO has not been disproved. And on the other side, sample data is strong. HO will be disproved in that case, in which case the HA is correct. In a judicial system, the jury decides if the sample evidence is enough to prove the defendant is not innocent. Innocence is the assumption throughout the trial, and then when the sample evidence is provided, the jury chooses whether or not that sample evidence is enough. In a hypothesis test, we do something very similar. We take sample data, we compare that sample data with population data, and if we have a big difference between our sample data and population data, we call it significantly different. Then the alternative hypothesis will be the winning decision. If not, then the null hypothesis will be the winning decision. Rare events, when they occur in hypothesis testing, when we calculate probabilities and they are rare, these are rare events, they indicate that there is a significant difference between the population parameter and the sample statistic. Rare events indicate that HA is correct. Okay, so HA will be the winning decision in that case. Let's look at an example and try to make a decision as if we were a jury. A new diabetes management program claims to lower the population mean fasting blood sugar level for participants. For the general population not enrolled in the program, the mean fasting blood sugar level is, and we have 130, with a standard deviation of 10. Assume fasting blood sugar levels are normally distributed. A random sample of 40 participants in the new program has a mean fasting blood sugar level of 127. Okay, so we're given a sample mean, we're giving a sample size 40, and then we're given a sample mean of 127. Let's calculate the probability of observing a sample mean fasting blood sugar level of 127 or lower. So by calculating the probability here, we're calculating how common is it for us to find 40 people and have a sample mean blood sugar level of 127 or lower. And when we calculate this probability, we are going to assume the true population mean fasting blood sugar level is 130. So that's going to help us with our probability because we're going to be using normal CDF here, and we need to know the population mean. So how do we calculate a probability? We need to recognize that we're dealing with a sample and we're calculating the mean of, or we're looking for the probability that the sample mean is 127 or lower, and therefore the probability will be calculated using a sampling distribution. So we're going to find the probability, and then we're going to decide if we have a rare event. Does it appear the new program is effective? So we want to recognize whether or not this 127 is really a rare event. If it's a rare event, it would mean that it's significantly less than 130, and it would mean that this new management program is working. Okay, and it would mean that the program is effective. So let's take a look and calculate this probability. These are the important details that were provided in the problem. Mu, sigma, n, and x bar. We're finding the probability that the sample mean is less than or equal to 127. So since it's asking us about the probability of a sample mean, we need to use the standard error because we're working from a sampling distribution. Let's calculate the standard error with this formula. We're going to take the sigma 10 divided by the square root of n, which is 40. 10 divided by the square root of 40. We're going to round that to 4 decimal places. I'll do it on the calculator to show you. So 10 divided by the square root of 40 and 1.58. We're going to conventionally, we've been doing this, we round to 4 decimal places. 1.5811. Okay, so now that we have the standard error, we're going to go to normal CDF and we're going to plug in the lower and upper necessary to solve this problem. Let's go to our picture. Remember that the mean of a sampling distribution is the same as the mean of the population, and that had to be provided to us in this problem. So we have 130 as the center of our sampling distribution with a standard error of 1.5811. The probability that x bar is less than 127, we're going to put x bar to the left of center because 127 is less than 130, and we're going to calculate the area that extends down to negative infinity. Okay, so I'm going to be plugging into the calculator a low of E99, negative E99, an upper of 127, a mean of 130, and the standard error. And we're going to get an answer, 0.0289 or 2.89%. I'll do it on the calculator to show you. Normal, CDF, negative E99 to 127, 130, and 1.5811. Our probability is 0.0289, rounded to 4 decimal places. 0.0289 rounded to 4 decimal places, and turning that into a percent, it's 2.89%. So would you consider this a rare event? In order to figure that out, we need to be provided with a little bit more information. Let's talk about a p-value. The answer 2.89% can be interpreted like this. Assuming the true population mean fasting blood sugar level is 130, the probability of observing a sample mean fasting blood sugar level of 127 or less or lower is 2.89%. That's the meaning of the probability that we just calculated. We have to decide if that 2.89% is considered to be a rare event. If we say it's rare, then it would appear that the new program is effective. But we have to understand what rare means. How low does the probability have to be for us to classify it as a rare event? So you have to be given some extra information here to do this. There's a name for the probability we calculated right here, 2.89% or 0.0289. It is called a p-value. In hypothesis tests, we call the answer to the probability question a p-value, a probability value. So in this case, the p-value is 0.0289. And it turns out, as you would expect, the smaller the p-value is, the more rare that event is, and therefore the stronger the evidence that the new method is more effective. So it could be testing anything, testing a drug, a treatment, a vaccine, a new product, a new exercise plan. The smaller the p-value is, the stronger the evidence, whatever we are testing is truly more effective. So the p-value, 0.0289, we don't know if that's rare enough. So the problems have to provide us with more information, and that's where alpha comes in. It's a level of significance. Alpha is a level of significance, and it is a percentage, and it guides us on how small the p-value must be. Alpha will either be provided in the problem as 1%, which converts to a decimal of 0.01, or 5%, which converts to a decimal of 0.05. If the p-value of the sample statistic happening is less than the alpha provided in the problem, less than the alpha, then it's considered to be a small probability. It's considered to be a highly improbable rare event. And that's indication that the treatment you're testing is effective. When we are the jury and we make our decision, what we do is compare that p-value that we calculated to alpha, and we make our conclusion that way. So let's look at our p-value and alpha. Let's suppose that the problem told us or guided us to use a level of significance of 1%. So an alpha of 1%, a level of significance of 1%. We went on and we calculated our p-value, and then we compare our p-value to alpha. So looking at 0.0289 and looking at alpha of 0.01, we see that our p-value is not smaller than alpha. It's not small enough. If it's not small enough, it means that our sample data is not strong enough. The null hypothesis is not disproven when the sample data is not strong enough. So whatever we're testing, whatever new program, new drug, new medication, new exercise, what that is being tested, it means that it is not effective. Okay, so the jury would come out and say the p-value is not small enough. 0.0289 is not less than 0.01. The program is not effective at reducing blood sugar levels. And in that case, who wins? HO or HA? The HO wins in that case. We've not shown that there's reason to reject the assumption that the treatment doesn't work. But a problem could also provide a significance level of 5%. It will either be 1% or 5%. It can't be both. So if this problem happened to provide a significance level of 5%, we have a totally different situation. If we compare 0.0289 to 0.05, which is 5%, we see that our p-value is smaller than alpha. It is smaller than 0.05. When it's smaller than the alpha, when it's smaller than the significance level, we conclude that the sample data is strong. So this is not just our opinion. We're actually looking at the numbers here and seeing that the p-value is smaller than alpha. We get to disprove the null hypothesis. The sample results are considered to be significant. The new program, new drug, new treatment, new exercise for lowering mean fasting blood sugar levels is effective. Okay, so that's when the p-value is smaller than alpha. We have an effective treatment. So the jury now comes to the conclusion that the p-value is small enough, 0.0289 is less than 0.05, the program is effective at reducing blood sugar levels. So when you look at who wins, HO or HA, in this case, HA wins. So p-values, we just did an example where the p-value was on the left-hand side because we were dealing with a probability that asked for finding a probability that went down to negative infinity. It said less than a particular x bar. Well, sometimes you have to find the probability on the right, more than a particular x bar. So sometimes you will be given a situation like this, and other times you'll be given a situation like this. And there is a third type of hypothesis test that I'm not going to cover in this semester, but it does have p-values on both sides. These are called bidirectional hypothesis tests, and I'm not going to be covering those types, but they are valid and they are out there if you want to look them up. So the p-values that I'm going to be using are either going to be in the left tail or the right tail of the normal distribution, and it all depends on the testing scenario. For the glucose levels, for testing glucose levels are lowered, giving a new treatment, we worked with the p-value on the left because we were dealing with x bar on the left side of 130. It was a 127. And we were looking to see if the probability was lower than 127. But if we had a different type of situation, in this case, let's look at an example where we're trying to improve cardiovascular endurance through some new treatment or exercise plan, and we want to see if it's increased. Well, that would mean that we'd have our mean in the center, and the X bar hopefully would be greater than that mean, and we'd be testing for an increase in cardiovascular endurance. We'd be testing on the right-hand side, so our p-value would be on the right in that case. You have to read the problem carefully to decide which side your p-value is on. It's going to make a big difference in your final calculations. If you put your p-value on the wrong side, your probability is going to be wrong, and your conclusion will then be wrong. Okay, let's look at p-values on the same side, but clearly one p-value looks smaller than the other p-value. So over here, this X bar that cuts off the shaded area has this value of A, and in this other example, the X bar that cuts off the shaded area has a value of B. So the area to the right of A is this p-value. The area to the right of B is this p-value. A small p-value indicates a rare event. Smaller p-values indicate stronger evidence that the assumption about the population in the null hypothesis is incorrect. So in these two pictures, the p-value on the left has the smaller area, and therefore it gives stronger evidence that the population assumption was incorrect. The area is smaller, the probability is smaller, the event is rarer. We say that the event on the left is more significant. This is a more significant p-value than the area on the right. We say this is less significant. So to put this into context, imagine that you have two exercise programs that claim to increase cardiovascular endurance. and one gives you this result, and the other one gives you this result, which exercise program would you choose? And you're going to choose the one that's more significant. And the reason why, if you look at the area, the smaller area on the left side here, or I'm sorry, I meant to say on this left example, the smaller area means that this X bar is further to the right than this X bar. So imagine the mean. This is the cardiovascular endurance if you do nothing. This is the cardiovascular endurance if you do nothing. If you go with this treatment, I'll call it treatment 1, it increases in the sample, it increased cardiovascular endurance this much. And in this sample, T2, treatment 2, it increased cardiovascular endurance this much. Looks like there's a bigger increase in treatment 1. The bigger increase in treatment 1 ended up with a smaller p-value. It's a more rare event. It's more significant. It's less common for you to end up with results like this, which makes it more extraordinary, and therefore the treatment is more effective than treatment 2. So interpreting the p-values. If a p-value is less than 0.01 or 1%, we say it's a very significant p-value. If it's less than 0.05 or 5%, we say it's significant. If it's greater than 5%, we're going to say it's not significant. So this is an example of a p-value that would be greater than 5%. That is a not significant statistical result. So sometimes we classify them in the problems. You'll see the wording in the problems ask for that sometimes. So when we look at our p-value, it gives us enough information to make a conclusion for our hypothesis test. Once we decide that the p-value is very significant, significant, or not significant, we can make, it should say, our conclusion. There are two types of hypotheses, remember, HO and HA. HO, we said that whatever we're testing, treatment, vaccine, drug, product, has no effect. And HA, the treatment has an effect, is effective. When you make a conclusion, you're only going to state one of the two following conclusions. Either you're going to state reject HO, which is reject the null hypothesis and accept the alternative hypothesis, or you're going to state that you're failing to reject the null hypothesis. And these are the way we phrase these conclusions. We're not going to change the way these are phrased. This is the established, accepted way to end a hypothesis test. Either reject HO and accept HA, or fail to reject HO. If the p-value is less than the significance level, the conclusion is reject HO and accept HA. This is like finding the defendant guilty or stating a treatment is effective once sample evidence is examined. So you find your sample evidence, you examine it, it looks like it works, and therefore you make the conclusion that the treatment is effective. You're rejecting what you said in the null hypothesis and accepting what was stated in the alternative hypothesis. Same with defendant being found guilty. You're rejecting the innocence that was claimed in the null hypothesis, and you're accepting that the defendant is guilty. If the p-value is not less than the significance level, the conclusion is fail to reject HO, fail to reject the null hypothesis. You don't have strong sample evidence in this case. This is like stating that the defendant is not guilty. So you've gone through the trial, you've looked at the evidence seemed weak, so the defendant is not guilty. You have failed to reject what you stated in the null hypothesis, which was that the defendant was innocent. In testing medical claims or product claims, we will be saying that the treatment or the product is ineffective when we fail to reject the null hypothesis. We don't say that the defendant is innocent in when we fail to reject the null hypothesis. We don't say that we are accepting the null hypothesis. We say that we fail to reject it. So we say the defendant is either not guilty or guilty. We say that we fail to reject the null hypothesis or we reject the null hypothesis. So the following, what we're going to see in the following lectures on the hypothesis testing procedure is a pretty standard set of steps that we're going to go through. We're going to start with the null and alternative hypotheses, and then we're going to end with a conclusion. So to start, we do the words for our null and alternative hypotheses using the context of the problem presented. So that's step one. We're going to practice some of that in this lecture. Then we're going to do some additional statistical analysis, often involving finding the p-value. And the last step is making the conclusion. So let's do a few examples for formulating hypotheses. This is just step one. And then in the next lecture, we'll go through the whole procedure from beginning to end. So let's be given a scenario first. A hospital administration believes that the population mean weekly work hours for their nurses is greater than 40 hours per week due to increased patient load. They want to test whether this belief is supported by data. A random sample of 50 nurses at the hospital is surveyed, and their weekly work hours are recorded. Okay, so I'm underlining some important stuff here. The null and alternative hypotheses for this situation is going to use this underlined information so we can formulate these. So in our null hypothesis, we always state that there is no change, there is no effect. Whatever we're testing is non-effective. Okay, so we're going to do that here, and we're going to discuss what each hypothesis implies in the context of the hospital's claim. So the hospital thinks that nurses are really working more than 40 hours a week because there's more patients. The null hypothesis in this case is going to state that the population mean weekly work hours for nurses is 40 hours a week. So our null hypothesis is always a statement that there is no change from the population mean, from the current established population mean. We also write it in symbols. So the population mean is 40, mu is 40. This null hypothesis implies that the increased patient load has not led to a significant change in work hours, that the nurses are working no more than the standard 40 hours per week, work week. So the null hypothesis says that there's no difference. The alternative hypothesis, this is where we have our counterclaim, and this is where we state that the population mean weekly work hours for nurses is greater than 40 hours. This was that counterclaim that was presented in the scenario. Symbolically, we're going to write mu greater than 40 hours. And what this means, this alternative hypothesis supports the hospital's belief that patient load has increased nurse work hours, that the average work hours are higher due to increased patient load. Testing these hypotheses would involve collecting data from the sample, calculating a test statistic, determining whether there is enough evidence to reject HO in favor of HA. So we would look at all these nurses' surveys, we would calculate the amount of hours they work, and we would see if it's significantly greater than 40. Okay, let's look at another scenario. We're not going through the entire problem. We are just setting up the null and alternative hypotheses in this lecture. A patient advocacy group claims that patients in rural areas spend less than $120 monthly on prescriptions on average. To test this claim, a health researcher collects data from a random sample of 50 rural patients. State the null and alternative hypotheses for this situation and explain the context of each hypothesis. Okay, so this information that I'm underlying here is going to help us with our counterclaim, but our null hypothesis is going to state that patients don't spend any less than 120. So the null hypothesis, the population mean monthly spent on prescriptions is 120. I should actually add here, population mean monthly spent on prescriptions for patients in rural areas. I should add that. For patients in rural areas is 120. Mu equals 120 is our null hypothesis. And what this means is there is no difference in the amount spent on prescriptions for rural patients from the standard value of 120. 120 is the population mean, and it's the same for rural patients, 120. So our null hypothesis states what's currently believed to be true. It is 120. Now, if we look at the counterclaim, the alternative hypothesis, this is where we start to indicate the direction. The population mean spending on prescriptions, I'm going to also add here, for patients in rural areas. Rural areas is less than 120. Mu less than 120. This HA supports the advocacy group's claim. There is a difference in the amount spent on prescriptions for rural patients from the standard value of 120. The goal is to determine whether the sample data provides enough evidence to reject HO in favor of HA. Okay, HO versus HA. If our sample data shows that rural patients spend significantly less than 120, then our winner will be HA. If our sample data shows that rural patients don't spend significantly less than 120, our winner will be HO. And this is all going to be used by comparing P to the significance level alpha. Okay, so that concludes this lecture. I'm stopping here, and in my next lecture, I'm going to take you through the entire hypothesis testing procedure where we look at the data and we do make our final conclusion. And it involves a series of steps that I'm gonna adhere to for all types of hypothesis tests. So if this was helpful, let me know. And if you have any questions, you can email me. I'm going to move on to the next lecture now. So if you're interested, go ahead and watch the lectures. I think it's 18 next. Okay, have a good one. Thank you.